Dear students, a warm welcome to everyone. So in our last video lesson, in the chapter of electrostatics, we tried to understand what is Gauss theorem and we tried to prove it. And in today's video, we try to find the electric field intensity due to a point charge, and we also try to find the electric field intensity due to a charged spherical conductor, and we also try to find the electric field intensity due to a charged sphere by using Gauss law. Okay, fine. So without much delay, we just move on to our next slide. So the applications of Gauss law. So what is Gauss law? That we already have done it, right? The flux, the total flux passing through a closed surface is always equal to 1 by epsilon 0 times the charge enclosed by it, right? So, and the mathematical equation is found to be integral E dot ds is equal to q by epsilon 0. So now this Gauss law will help us to find the electric field intensity of certain complicated system of charges very easily. So that means by using law, we can easily find the electric field intensity of a certain system of charges. But to find that electric field intensity, we need to follow certain steps here. And what are the steps that I already have written over here? So first of all, we need to have the system of charge because of which we have to find the electric field intensity, right? So to find the electric field intensity of such a system, the first point that we have to do is we have to choose the point P where we want to find the electric field intensity. So that is the first step that you have to remember. And after choosing that point, you have to construct a Gaussian surface around the charged body which passes through the point P. So that is the second step that you need to remember. And after construction of the Gaussian surface, you have to choose a small area element ds at point P where you are finding the electric field intensity. And after doing this, you have to draw the directions of electric field intensity and also the area element that you have chosen at point P. And once the construction part is over, you just directly apply the formula for the flux that is passing through the small element that you have chosen, and on integrating it and doing some little mathematics, you can easily find the electric field intensity due to a system of charge that has been given to you. Anyway, these are the points that you need to remember. These are the steps that you need to follow to find the electric field intensity of a system of charge. Okay, so anyway, to make it clear, we just move on to our next slide. Okay, so this is the first system of charge whose electric field intensity we want to find by using Gauss law. So the first one is the electric field intensity due to a point charge. Here E is electric field intensity, so please remember. So now we try to find the electric field intensity due to a point charge by using Gauss law. So please remember this one. Okay. So what are the steps that you have to follow? Please, I hope you remember it. But even if you don't remember it, so don't worry. So we are going to follow each and every step slowly and in detail. Okay. So now these are the steps that you need to follow while using Gauss law. So the first one. So let us assume that this is the point charge. This is the point charge plus Q which is present at O, because of which I want to find the electric field intensity. And remember, by using Coulomb's law, we already found the electric field intensity, but here we are trying to find the electric field intensity of this plus Q charge using Gauss law. Okay, so that you remember it. Okay, now fine. So what are the steps that we have to follow? So now the first step is that choose the point P where you want to find the electric field intensity at a distance of r from the charged body system. So now this is your system. It's a point charge, and we want to find the electric field intensity due to this. So for that, what is the first step here? We have to choose the point P where you want to find E, right? So you can choose any point around it, right? For example, I can choose this point P here, or I can choose the point P here, or I can choose the point P here. Anywhere that you want, you just choose a point P where you want to find the electric field intensity, and take that point P and let us, that means you have to choose the point P, and you have done it, and let us take the distance of that point P from this charge as r. So like that. So you have to choose the point P, and also you have to choose the distance of point P from the charge as smaller. So you can take the distance by any symbol that you want. You can take it as capital R, you can take it as small r, whatever it may be, but for convenience in our coming derivation and also in this derivation, I always choose that point P from the charged system by smaller only. Okay, so please remember it. Anyway, I just erase everything. So this is the point charge whose electric field intensity I want to find. For that, I have to choose a point P in such a way that it is at a distance of smaller from plus Q. Okay, so let us just choose that point P here. So let us assume that this is the point P where I want to find the electric field intensity, and I have taken the distance of this point P from this charge is smaller. Okay, fine, I hope it is clear. So now next step. So now you have to draw a symmetrical closed surface, which we call it as Gaussian surface, around the charged body which passes through point P here. Anyway, this is the charged system now, right? So it's a point charge. So now what I have to do is that I have to construct a closed surface, okay, around this plus Q in such a way that it passes through point P. So while doing the Gauss theorem, while doing the proof of Gauss law, even there also I have constructed a Gaussian surface, closed surface, right? Here also what we have to do, we have to construct a closed surface around plus Q in such a way that it has to pass through point P. Is that clear? So that is the condition. And for convenience, what we do here is that closed surface is drawn here as a symmetrical one. Okay. So while doing the proof of Gauss theorem, we have constructed an unsymmetrical closed body, right? Closed surface, closed surface. But here, for convenience and for making the calculation easier, we construct a symmetrical closed surface here. Okay. So in this case, the symmetrical closed surface will be a sphere of radius r. What is the meaning of spherical symmetrical? Symmetrical means if you stand at Q, and if you see in all the directions, the closed surface should be at equal distances. This we call it as symmetrical. That means the environment around plus Q must be same. So that is the meaning of symmetrical here. And you can construct unsymmetrical also, but the calculation becomes complicated. And for that reason, we have to construct a symmetrical closed surface here, and in this case this will be sphere, not circle. So please remember, because plus Q is present in some space, right? And point P you can choose anywhere around it, and that means whatever the closed surface that you construct here, it becomes a sphere, which is a symmetrical one. Okay, so now let me erase this one, or okay, let us just continue this. So this becomes, this is the Gaussian surface that I have constructed, and remember we call this as Gaussian surface. Okay, you always remember the surface that you are constructing is called as Gaussian surface. You are constructing it, actually it is not there. Okay, actually it is not there, you are constructing it. Okay, so that you have to remember. It's an imaginary surface, it's actually not there. It's an imaginary surface that you are constructing in such a way that it passes through point P. So this is also called as Gaussian surface, and this is also called as imaginary surface. So you just use whatever the word that you want, but in general we call it as Gaussian surface. Okay, so now let us move on to our next one. Okay, so now after constructing the Gaussian surface, a symmetrical Gaussian surface, you have to choose a small area element ds at point P. Remember, where you have that means where you have chosen the point P, at that point P you have to construct a small area element ds here. Okay, so that ds I have chosen this one, so please check it out. So this is the area element that I have constructed at point P. Okay, I hope it is clear to you, and let us move on to our next step now. So this one, so after constructing the area element at point P, you have to draw the directions of electric field intensity and also ds at point P. So what is E here? Electric field intensity, and ds means area vector. You already know, right? So area vector will be always perpendicular to the area, right? So now in this case, since it is the positive charge at point P, the electric lines of forces will be coming out like this. Okay, I hope it is clear to you. I hope you remember what we have studied in case of electric lines of forces, right? So at this point the direction of electric field will be outside, and this is ds, right? Okay, so ds vector will be perpendicular to ds, that means even ds will be directed in outwards. So please check this out, even ds will be directed in outwards. Okay, so now I hope it is clear to you. So now at point P I have constructed the directions of E and ds. Is that clear? And in this case the directions of E and ds will be along the same direction, that means the angle between E and ds will be 0. And let us just move on to this one. So anyway, even here you can see the directions of E and ds will be along the same direction, which is in outward direction. And the next one, so write the mathematical equation of flux through ds at point P. So you know the equation for flux, right, which is E dot A, or anyway in this case the flux through ds we write it as E dot ds. So you know this equation, right? So that we already have studied it. So just write, remember this is plus q, right? Since this is plus q, electric lines of forces will be coming out in all the directions like this. In all the directions the flux will be coming out. So now this is ds that we have chosen. Even through ds some flux will be coming out. Is that clear? Some flux. So now that flux we write it as E dot ds. So E dot ds is the flux that is coming out of this area element. So that means some lines of forces will be coming out of ds also. That number of lines of forces we call it as E dot ds. Okay, so fine. So now this is the flux that is coming out of the ds element. So the number of lines of forces that are coming out of this ds area element that we have chosen at point P is denoted by d phi e, which is equal to E dot ds. So now if you want to find the total number of lines of forces that are coming out, what you do, you just do the integration part, that's it. Okay, so now, so this is d phi e, which is the flux that is coming out of this small area element that you have chosen. To find the total electric field, total electric flux, what you do, you just integrate this equation. If you integrate it, what you get phi e. So I can write phi e as integral d phi e, and where d phi e is from equation, I can write it as E dot ds. So E dot ds, remember these two are vector quantities. Okay, so I can write this as E dot ds, which is E ds cos theta, where theta is angle between E and ds. So here the angle between E and ds is found to be 0, and hence cos 0 becomes 1. So here I have written here, so please check it out. Phi e is equal to integral E ds cos 0, and integral cos 0 is 1, you know that. So that means phi e becomes integral E ds. So now E is a constant, you can just take it out. If you take it out, E integral ds, it becomes E integral ds, and integral ds is the total surface area of this sphere. Remember, ds is the part of this Gaussian sphere, right? This is your Gaussian sphere, ds. ds is a small area element of the sphere that you have constructed. Small area element of the Gaussian sphere that you have constructed. Now integral ds means the total surface area of the sphere. So the total surface area of the sphere of radius smaller is given by 4 pi r square. I hope you will remember this formula, so please remember it. So anyway, so finally I get the total electric flux that is coming out of this Gaussian sphere is coming out to be E times 4 pi r square. Okay, so let us take this equation as 2. So now I just have a doubt here. So anyway, in this equation you must have, that means already some of you might have observed here. So I am taking E out of integration here in this step, not here. Why is that so? It is because here the electric field intensity is written by E bar, so please check it out, but here there is no bar here. So that means here E bar represents the electric field intensity in terms of vector quantity, whereas this E denotes the magnitude of electric field intensity. So if you observe here, at point P the electric field intensity direction is outward, right? If the same point P is chosen somewhere here, at this point the direction of electric field intensity will be in some other direction. If you choose the point P here, the electric field intensity direction will be in downwards, like that. Okay, so at different points the direction of electric field intensity will be different, but its magnitude will be constant, because if you choose this point or this point or this point, they are all at the same distances, right? This is also R, this is also R, and so on. So if the point P changes, the direction of electric field intensity changes, but its magnitude remains constant, and hence here at this point E is not constant here, because direction of E is changing, but at this point E is constant because this E is just the magnitude of electric field intensity, and hence you can take it out. So I hope you got it. So at this point you cannot take E outside the integration, but at this point you can take E outside the integration because it is constant. I hope it is clear to everyone. Anyway, just I am erasing everything. So now you know equation 1, which is flux that is passing through the small area element that you have chosen, and this is the flux, the total electric flux that is coming out of this entire Gaussian sphere. Okay, so now let us just move on to our next one. But we know that from Gauss law, flux, total electric flux coming out of a closed surface. Remember, this is a closed surface. It is closed, right? This is closed surface. So the total electric flux that is coming out of the closed surface is equal to 1 by epsilon 0 times Q, charge enclosed by. That means the charge that is present inside this closed surface is plus Q, right? So that means you get Q by epsilon 0. So this is Gauss law, which is equation number 3. You know this, right? Okay, so this is flux passing through ds. This is total electric flux, okay, of this system, and this is from Gauss law. Equation 3 is the mathematical equation that you get from Gauss law. Anyway, if you compare equation number 2 and 3, this is 2 and this is 3, right? So on left hand side you have phi E, total electric flux. So since on left hand side you have total electric flux, which is phi E, on right hand side also you have E 4 pi r square, and here you have Q by epsilon 0. That means the right hand side quantities or terms must be equal here. So since they are equal, what do you get? You get from equation 2 and 3, what do you get? You can write it as E times 4 pi r square is equal to Q by epsilon 0. And if you send 4 pi r square to right hand side, what do you get? You get the electric field intensity at a distance r here. So at a distance r, the magnitude of electric field intensity is found to be Q by 4 pi epsilon 0 r square. I hope you remember the formula of electric field intensity due to a point charge that we already found by using Coulomb's law. There, by using Coulomb's law and by the definition of electric field intensity, we already found the formula for electric field intensity, which was coming out to be Q by 4 pi epsilon 0 r square. Even here, the electric field intensity of a point charge. What is point charge here? Q. So the electric field intensity of point charge Q at a distance of r, this is distance, at a distance of the electric field intensity of Q is found to be E is equal to Q by 4 pi epsilon 0 r square. But remember, we have found the electric field intensity of this point charge by using Gauss law. Okay, I hope it is clear to everyone. So now by using Gauss law, what we have done, we have found the electric field intensity due to a point charge. Now let us move on to our next very important topic for your board examinations. This question you got it many times. Okay, so anyway, our next topic is to find the electric field intensity due to a charged spherical conductor. This we also can call it as hollow sphere. We can call it as a hollow sphere or electric field intensity due to a charged spherical conductor, if it is a conductor. Okay, so charged spherical conductor, there are two cases here. We can find the electric field intensity due to charged spherical conductor, and we also can find the electric field intensity due to a charged sphere. There are two topics. You may get confused, but please don't get confused. They are different. Charged spherical conductor is different, charged sphere is different. What is that difference we will discuss. Anyway, so charged spherical conductor. So this is a charged spherical conductor that I am considering. Okay, so now this is the system that has been given to us, which is a charged spherical conductor. So it's a conductor. It's a spherical conductor of radius capital R. So please check it out. This is the charged system that has been given to us. So now let us assume that we have given a charge which is plus Q to this system. So what happens, since it is a conductor, the entire charge resides on its surface. Okay, so that means inside this conductor there will not be any charge. There will not be any charge. So please remember it. It's a conductor. Whatever the charge that you give it to it, the entire charge spreads on its surface. It uniformly spreads on its surface, and inside this conductor there will not be any charge. So please that you try to understand, and hence all this charge is drawn over on its surface. So please check it out. Okay, whatever the charge that is given to this spherical conductor, that is uniformly distributed on its surface. I am repeating again and again because this point is very important while doing the derivation. Okay, so now fine. So this is the charged system that has been given to us. Now I want to find the electric field intensity due to this charged spherical conductor. So again, what we have done in our last topic, we have to follow the same steps. You should not miss them. Is that clear? Whatever the steps that we have followed already, you have to follow the same steps. So don't even miss a single step, and you follow those steps, automatically the entire topic will be very much easier to you. Okay, so what is the first step that we have followed there? Okay, so we have chosen, first of all we have to choose a point B where you want to find the electric field intensity. So please remember that one. You can even see there. Okay, choose the point B where you want to find the electric field intensity at a distance of r. That means first of all choose a point P where you want to find the electric field intensity. So now let us assume that this is the point P that I have chosen where I want to find the electric field intensity. Is that clear? So this is the point P where I want to find the electric field intensity. So now let us assume that the distance of this point P from this spherical conductor is smaller. Remember, the distances are always measured from the centers. Okay, so the distance of point P from this spherical conductor is measured from the center. So this one. Okay, from here to here. So from here to here. So please check it out. From here to here. Is that fine? Or else if you want to just check it, okay, so let me take some other color, it helps you. Okay, so this one. Is that clear? So the distance of point P from the spherical conductor means the distances has to be measured from the centers. Okay, I hope it is clear. I just erase it. So I have chosen point P where I want to find the electric field intensity, and I have taken its distance by small r. So remember, here in this derivation there are two r's. One is small r, another one is capital R, where capital R is the radius of the spherical conductor whose electric field intensity we want to find, and the small r is the distance of point P from the spherical conductor where we want to find the electric field intensity. Okay, fine. So point P is chosen. Next, what we have to do? We have to construct the Gaussian surface, which is symmetrical again. Okay, is that clear? What we have done in our last topic? we just repeat the same. Not only in this topic, next we try to find the E due to charged sphere. There also we follow the same steps. Next we have to find the electric field intensity due to cylinders. There also we try to find. So please remember these steps. They are very easier. You just follow these steps, the entire derivation will be easy. Okay. So now you have to construct a closed surface, which we call it as Gaussian surface. In this case, to make it easier, we construct the symmetrical Gaussian surface here. So what kind of Gaussian surface we get here? Since it has to be symmetrical, again here we get one more sphere, which is a Gaussian surface here. Okay, so now the Gaussian surface comes out to be this one. So please check it. So remember, this sphere which is shown in red color is the real sphere that we have, on which the charge is present. But this one, the outer sphere which is drawn with pink color, light pink color, is the Gaussian sphere that we have constructed. Okay, so let me write it down here. So this is Gaussian sphere. This is Gaussian sphere. So this is imaginary sphere. Actually it is not there, but we are trying to imagine it, we are constructing it. It is the Gaussian sphere. Okay, and then next what step we have to follow? So we have constructed the Gaussian sphere here. It's not circle, it's a sphere. Okay, so now we have to draw a small area element at P, right, which is ds. So now as you are seeing here, choose a small area element ds at point P. So at point P you have to choose a small area element ds. Okay, so we have chosen here. So let us assume that this is the small area element that we are choosing at point P. What is the next step that you have to do? You have to just draw the directions of electric field intensity and area vector that you have chosen at point P. So that is our next step, right? So draw the directions of E and ds at point P. So this is point P, and you have to draw the electric field intensity direction and also ds, which is area direction at point P. So what will be the directions of both E and ds? As we already have discussed, at point P the directions of E and ds will be same, which are in outward direction, right? So just check it out. So these are the directions of E and ds at point P. We already have discussed it. So that means here theta becomes 0. Here theta becomes 0. I hope it is clear. So now what next? So fine, we have found the directions of E and ds at point P. Now what you have to do? So you know that since it is a positive charge, it's a positive charge, right? The entire charge is positive. So all the electric lines of forces will be coming out in this way, in all the directions, like this. All the electric lines of forces, since it is positive charge, the electric lines of forces will be coming out in all the directions like this. So that means a few lines of electric force will be coming out of ds also, right? So that means few lines, they will be coming out like this, right? Sorry, like this. So that means a few lines will be coming out of ds, and the number of lines of forces that is coming out of ds, we call it as the flux that is passing through ds. So now what you have to do to apply Gauss law? First of all, we have to write the number of lines of forces that are passing through ds, which is taken as E dot ds, right? We already have done it. So take that one. So this is write the mathematical equation of flux that is passing through ds at point P. Okay, so what is that formula? So this is the formula that we are writing. So here it is written over here. So please check it out. Okay, or else I will erase everything. It will be same. So this is the flux that is passing through ds, which is written as d phi e, which is equal to E dot ds. Anyway, so now you know that flux that is passing through ds. Now to find the total flux, what you do? You just integrate this equation. Okay, so that will be there in our next slide. So now this is the flux that is passing through ds, or that is coming out of ds. Okay, so that is taken as equation 1. This is d phi e, which is equal to E dot ds. To find the total flux, what you get? You just integrate this equation. If you integrate this equation, what you get? You get phi e. So now I can write phi e as integral d phi e, which is equal to integral E dot ds. Okay, this is a vector notation, so please check it out. Since it is vector quantity, E cannot be taken out of this integration, because electric field intensity is not a constant quantity, because its direction changes if point P changes on this Gaussian sphere, but its magnitude will be constant, so please check it out. Okay, and hence since E is not constant when it is a vector, you cannot take it out. So anyway, expand it. If you expand it, so this I can write it as remember, this is notation is different. Here S is written, it is circle is mentioned. I already discussed these two quantities are same, so I am not repeating it once again, so please check it. So I can write E dot ds as E ds cos theta, where theta is the angle between electric field intensity and area vector. Okay, so now you have to find theta. Once you know theta, the mathematical derivation will be very much easier. So anyway, from the figure it is clear that theta is 0 here, because E and ds are along the same directions. Theta is 0. Since theta is 0, substitute that. So what you get cos theta, that means cos 0 in place of cos theta. So that means I can write phi E as integral E ds cos theta becomes cos 0, but you know that cos 0 is 1. Since cos 0 is 1, you just substitute 1. If you substitute 1, you get integral E ds, where E is constant now, because E is the magnitude of electric field intensity, which is constant, because here the Gaussian sphere that we have constructed here is a symmetrical one. Since it is a symmetrical one, even if point P changes, its distance remains same. What happens, for example, if point P is here, what happens, the distance of this point P from the spherical conductor or from the center of spherical conductor remains same, right, which is smaller. Here also smaller, here also it becomes smaller, and hence E will be constant here. Since E is constant, you can take it out. So if it comes out of this, you get E integral ds, whereas integral ds is the total surface area of Gaussian sphere. So please check it out. Integral ds is the total surface area of this sphere, which is Gaussian sphere, because ds is part of the outer sphere, right? ds is the part of outer sphere, and the radius of outer sphere is smaller, and hence integral ds becomes the total surface area of the outer sphere. So the radius of outer sphere is smaller, and hence the total surface area of outer sphere becomes 4 pi small r square. Most of the students get confused here, because in this derivation, in this topic, we have two r's, one is small r, another one is capital R. So please, you should not get confused. So the total electric flux becomes capital E times 4 pi small r square. So let us take this equation as equation number 2. Let me erase everything. So now from equation 2 and from equation 1, if you, sorry, not this equation 1, forget about it, just erasing it. So this is equation 2, where we found the total electric flux that is coming out of this Gaussian sphere, right? So now, but from Gauss law we know that phi is equal to integral E dot ds. You know this one, right? Phi is, that is the total electric flux that is coming out of a closed surface, is in mathematically written as integral E dot ds is equal to 1 by epsilon 0 times the charge enclosed by the closed surface. So this is our closed surface now. This is closed surface, and we have found the total flux coming out of it. How much? This one, which we get it from equation number 2. The flux that is coming out of this closed surface is E times 4 pi r square, and if you apply Gauss law, what you get, the total flux is equal to 1 by epsilon 0 times the charge enclosed by it. That means the charge that is present inside this closed surface is how much? Plus q. So that means if you apply Gauss law to this system, we get phi is equal to integral E dot ds is equal to 1 by epsilon 0 times the charge inside that closed surface becomes q, and hence from Gauss law we can write to this system the mathematical equation as integral E dot ds is equal to q by epsilon 0, which is equation number 3. So on left hand side, this we already found from equation 2, right? So this is nothing but phi E, which is E times 4 pi r square. So if you substitute equation number 2 in equation number 3, what you get E times 4 pi r square is equal to q by epsilon 0. And if you send 4 pi r square to right hand side, you get E is equal to q by 4 pi epsilon 0 r square. So this is the electric field intensity that we have found due to this charged spherical conductor. But remember, so this point P was outside the conductor. So remember, this is the conductor on which plus Q amount of charge is there, and we are trying to find the electric field intensity of this charged spherical conductor at a point P which is present outside the sphere, right? Outside the sphere, this is the charged sphere that we have. This is our system, and we are trying to find the electric field intensity due to this system at a point P outside this charged spherical conductor. So that means from the diagram it is easily seen that small r is greater than capital R. So this is the mathematical representation of the point P where you are trying to find the electric field intensity. That means whatever the derivation that is written in this slide, the total electric field intensity that we are trying to find is at a point P which lies outside the sphere. So please check it out. So this is the first case that we have done. So in this slide we have found the electric field intensity due to a charged spherical conductor at a point P outside the sphere, outside the spherical conductor. So now you can find the electric field intensity at two more points. One is if this point P lies on the surface, and if this point P lies inside the surface, what will be the electric field intensity? Those things also we try to find. So let us move on to our next slide. So these are the 2 points where you want to find the electric field intensity, other 2 points. So here we have already found, that means in this diagram, so for example this is, remember the red colored sphere is our original cylinder, original sphere, not cylinder, my mistake, sorry. So this red colored sphere is the charged spherical conductor whose electric field intensity we want to find. Is that clear? So and this sphere which is mentioned with light pink color is the Gaussian sphere. Okay, so this Gaussian sphere is the one which helps us to find the electric field intensity at a particular point. Where you want to find the electric field intensity, even at that point only this Gaussian sphere will be there. Anyway, so without much confusing you, so now when point P lies on the surface of this sphere, what happens? For example, if point P lies exactly at this point, what happens? Small r becomes capital R, right? So that means both spheres coincides with one another. If point P lies exactly on this sphere, for example, if point P is here, what happens? This small r becomes capital R. So this becomes small r becomes capital R, right? So that means you just substitute capital R in place of small r. You will get the electric field intensity at a point P on the surface of this sphere. Okay, so fine. When point P lies on the surface of this sphere, then what happens? Small r becomes capital R, as we already have seen it. Even here also you can see this is Gaussian surface. Okay, so that means if point P lies inside the charged spherical conductor, this is the diagram that you get. But if point P lies on this sphere, what happens? These two spheres coincides with one another, right? That means if point P is here, so this is capital R, and this also becomes small r. So when P lies on the surface of this sphere, the mathematical denotation becomes small r becomes capital R. Anyway, at a point P outside this sphere, we already found which is found to be electric field intensity, which is given by Q by 4 pi epsilon 0 r square. But if P lies on the surface, what happens? Small r becomes capital R. So that means when P lies on the surface of this sphere, the electric field becomes Q by 4 pi epsilon 0 capital R square. So let us take this equation as fourth equation. Now let us try to find the electric field intensity at a point P which is inside the sphere. So if point P, so this is the diagram which represents the third case. Okay, if point P lies, this is our charged spherical conductor which is denoted with the red color. So now if point P is present inside the sphere, so here this is the point P which is present inside the sphere. We already know that from the center of the sphere the distance of point P is taken by small r. So that means if you just observe the diagram, in this case small r becomes smaller than capital R. Okay, in this diagram small r is found to be less than capital R. So this is the mathematical denotation. Physically you can say that when P lies inside this sphere, small r becomes less than capital R. So that you just check it out. Anyway, you already know how to find the electric field intensity. You have to construct a Gaussian surface, symmetrical Gaussian surface which passes through point P, and then next choose small element ds, and then next find the directions of B and ds, and write the formula for flux and all those things. Again, same things are repeated here, so we need not do everything again and again. But the Gaussian sphere will be, this is the Gaussian sphere, so please check it out. This is Gaussian sphere. So now in this case, Gaussian sphere will be inside the real sphere. So that you just check it out. Real sphere means the charged spherical conductor is the system we have, and the Gaussian sphere is the imaginary sphere that you are constructing. So this Gaussian sphere will be present inside the sphere. That is the only thing that you need to understand. So now applying Gauss law, what you get, integral E dot ds is equal to 1 by epsilon 0 times charge enclosed by the Gaussian sphere. So this is the formula that you have to apply here. But remember, inside the Gaussian sphere, this is the Gaussian sphere, right? And this Gaussian sphere will be present inside the conductor. And in the beginning of this topic, I already told you that whatever the charge that is given to this conductor, the entire charge is uniformly distributed on its surface, and no charge will be present inside the conductor. And hence, inside this sphere, the charge that is present will be 0. Because whatever the charge that you give to conductor, it will not stay inside of it. It always comes out of it. Okay. So that means whatever the charge that is given to conductor, it will be present on its surface, not inside it. And hence, the charge that is present inside this Gaussian sphere, this is Gaussian sphere, right? I am mentioning once again. So this is the Gaussian sphere, and the charge that is present inside it will be 0. And if you substitute 0 in place of q, what you get? You get integral E dot ds is equal to 0. And you already know the formula for integral E dot ds, right? That is E times 4 pi r square. You already know that. And substituting and sending 4 pi r square to right hand side, what you get? You get E becomes 0. Electric field intensity becomes 0 here in this case. That means you choose any point inside the spherical conductor, any point, whatever the point that you want to choose, you just choose it. At that point, electric field intensity will be 0. So this is the electric field intensity that we have found due to a charged spherical conductor by using Gauss law. So remember, Gauss law helps us to find the electric field intensity easily. Okay, without much tension, you can easily find the electric field intensity by using Gauss law. But only what you have to do, you have to remember the steps that have to be done. Okay, so anyway, I thought of taking the other one also, which is I just wanted to find the electric field intensity due to charged sphere. But anyway, that we do in our next video. Okay, so we'll stop here. Thank you very much.